Welcome back, everybody. Hope you're having a great day. What I wanted to talk about today is number representation. Now, if you've ever used numbers or learned a language, what you simply have is a system that is agreed upon to represent certain words or numbers. That way, whenever we talk about something, we know what each other is talking about. We have a system that we all have agreed upon to use so that it's easier to communicate with one another, either with words or with numbers. Now, let's dive into numbers. With numbers, what we typically use is base 10, which is the number system you know. Every digit will either have 0 through 9 in it, and then every column is to a power of 10. Now, there are actually other ways to represent numbers, and as long as everyone knows about the system you're using, then everyone can understand those numbers. And we can use different numbers with different bases. Using a number system with a different base is like showing someone a different language. There's ways to represent exactly what you mean in that language, but you must understand that language to know what they mean. It's just like different number systems. You must understand those number systems to be able to know that what they mean in your language when you translate it back. Okay? Let's go over number representation. I made this quick PDF, which I'm going to have a link to in the description or in the comments that you can look at. And what it is basically the number system. What I have here is a basic equation of how numbers are calculated or how you may think of numbers being calculated. And that is that, let's say I have a number on the left here, and I made every digit a subscript number. So I have M0, M1, M2, M3. Think of that as being like 1,234 like I have below. Now, to actually calculate the numerical meaning of this number, what I do is I take M0 all the way on the right here and times it by the base of whatever number system I'm using. The base of a number system is how many numbers I'm allowed in each digit column. So let me show you guys an example. But what it means is how many numbers you can use in each column, like I said before. For instance, in base 10, you can only use 10 numbers for each digit. You have 0 through 9. Those are 10 numbers, by the way. 0 counts. So in a number like 1,234, you have only 10 choices to put in each digit. Now, here when you calculate your number, you're multiplying every digit by its base power respective to where it is. So the first digit, M0, is going to be multiplied by its base power, by its base to the 0 power. And then that base power goes up as you go to the left, as your number gets greater and greater, or as your digit has higher value. Something to also note, this works for decimals too. Decimals just count down. Decimals go from 10 to the negative 1, for example, 10 to the negative 2, and so on and so on. But we're just talking about the positive side of numbers for now. So let's look at a concrete example. We have decimal. Like I talked about, the decimal system can represent 0 through 9. And to calculate a number like 1,234, you simply take the digit and times it by its base power relative to where it is. So I take 1 and times it by 10 to the third. Note that we start calculating our decimal numbers starting at the power of 0. So 4 here is times our base power 10, and it's the least significant digit before the decimal, so we start our powers at 0. So 4 times 10 to the 0 isn't 0. Remember, anything times 10 to the 0, anything to the power of 0, is 1. So 4 times 1 is 4. Good. Then we add that with the next digit, which would be 3 times 10 to the 1. So we represent the tens column, as you'd commonly call that in school, by multiplying it by 10 to the 1, which is 10, obviously. So 3 times 10, which is 30. So this actually represents this column. Then I do 2 times 10 squared, which is 100. So that equals 200, represents this column accurately. Then I do 1 times 10 to the third, that equals 1,000. So you end up getting 1,000 plus 200 plus 30 plus 4 gives you our sum, 1,234. So that's beautiful, and that's actually a way to think of how you calculate each number. You may not think about that now because you do it all the time, or you can just look at the number, but this is how you're going to translate other numbers to other decimal systems, or other bases. Sorry, the decimal system is only the decimal system. So another kind of number system we can have is binary, which is base 2, meaning that each column, each digit can only represent 2 choices, and that's going to be 0 and 1. The reason because this is important to learn and why it's on my channel is that all computers, for now, run on binary. All a computer knows is ones and zeros. Everything, no matter how complicated it is distilled to a 1 or a 0. Now, again, I have a binary number here, 101011. Now, this is representing a regular number on the standard number line that we all know and love. And let me show you how you guys calculate it. You actually calculate it the same way we just did above. You just use a different base power, okay? So I made it more complicated here. Starting on the right, I have 1, and so I do 1 times our base power to the 0. Just like I did before. Instead of 10, though, we're using 2 as our base power because it's binary. So that gives me 1 times 1 because 2 to the 0 is 1. Then I do it here, and when we have another 1, so then I do 1 times 2 to the 1 is 2, so I have 1 plus 2. Then I get to the 0 for this column, I do 0 times 2 to the 2. 0 times anything is 0, so this column is kind of a wash. Well, it's just plus 0. Then I do 1 times 2 to the 3, 0 times 2 to the 4, 1 times 2 to the 5, and then when you do all this, you get a standard number 43. So binary can represent any number that this system can do. Now, in the language or in the format of binary, the way to represent a number like 1,234 would look completely different than the decimal system. And that's why it's important to understand the translation between the two systems, just like languages. Okay? Now, another system to finish this off is hexadecimal, which can be used to represent very big numbers in very compact sizes, as I say per the note. Now, hexadecimal is bigger than the decimal system. It's base 16. And so in base 16, you have 16 options for each digit. So you have your regular 0 through 9, which is 10 options, and then you have to represent basically 10, 11, 12, 13, 14, and 15, we decided to use letters. So A is 10, B is 11, C 12, D 13, E 14, and finally F 15. So this may be more complicated than binary in that you finally have to get over the fact that each digit can represent a number bigger than 9. Each digit can represent 15. But the way you calculate the numbers is the same as we've done before. Here I have a very weird looking number. I have A8F. What the heck? You always hate it when, the alphabet started, mingling with numbers. Then math gets really complicated. But it's really simple. And you do it the same way as our decimal system. Don't be scared. So we know we're in base 16. So we take the first column, F, which represents 15. We do 15 times 16 to the 0, because it's our base power. And that would be 15 times 1. Then I do 8 times 16 times 1, so that's a big number, right? And then our third column, we're already racking up a lot of power here, or just a lot of momentum. We have A, which is 10, represents 10 times 16 squared, so that's a big number. So just with 3 digits, I represented a number that's 2,703. So it's really easy to expand or make huge numbers from, small compact digits in hexadecimal. That's why they're commonly used to represent computer numbers, because computer numbers can get really big, in some cases very easily. That's why you see maybe in colors, if you've done CSS, it's like 0xFFF, because it represents a big number very easily, and there's a lot of color combinations. I hope you guys enjoyed this video. Let me know if I was very succinct and if my message was delivered clearly. Thank you guys.